Hello, this is Scott again. Just continuing my YouTube series on advanced analytics and data science. So, as you can see, last time we talked about data manipulations, and that was S15. The S designates that was Statistica. So that was just kind of a recap session. This time we're going to be talking about R. So we're going to be talking about forecasting with decomposition. And next time we'll continue in R and we'll be talking about forecasting with exponential smoothing. So if you've attended my sessions before, I normally focus on different tool sets, and then I have two different flavors. So some of the tool sets are R, Python, Statistica, Spotfire Data Science, etc. And then they're either tutorials. This one's more of a tutorial how to, and then I also have a series that are more application specific. You know, let's say multivariate statistical process control applied to engineering, or feature selection applied to, process engineering, or some sort of churn model or credit model or whatever. So let's get into forecasting with decomposition. So, while decomposition is primarily useful for, historical stuff, studying time series data and exploring historical changes, it can also be used for forecasting. So let's first assume that we have some sort of additive decomposition. Well, then we can write that additive decomposition like this, right? The adjusted time series, right? So the seasonal adjusting component is here, and it can be written in this expression, the time plus the residual, and then we have the seasonal component here as well. And then we can have the multiplicative, right? So just like we saw before, instead of adding these things together, it would be multiplying them together as well for multiplicative decomposition. So to forecast a decomposed time series, we forecast the seasonal component and the seasonally adjusted component separately. All right, so the S and the A, we forecast those separately, and that's what we apply. And so to forecast the seasonally adjusted component, the A sub T, any non-seasonal forecasting method could be used. For example, it could be, a random walk with drift. It could be Holt's method, which we're going to cover in an upcoming session, as well as ARIMA, which we'll see soon as well. Okay, so the first thing I'm going to do is I'm just basically going to use this low S, right? This STL method that we've talked about. I've already loaded the library, and I'm going to apply, a periodic window to the data, and I'm going to run that. And then I'm going to just auto plot the data here, and that's what I. So this plot here just shows the naive forecast of the seasonal adjusted electric equipment data that we've been using. So these are then reseasonalized by adding the seasonal naive forecast of the seasonal component. So what I want to do, and this is going to be made easy by using the forecast function, right? So I'm going to forecast using the naive method here applied to the STL object. So to do that, if I just run this code right here, then I get this. So the prediction intervals shown in this lower graph right here are constructed in the same way as the point forecast. That is, that the upper and the lower limits of the prediction intervals on the seasonally adjusted data are reseasonalized by adding the forecast of the seasonal component. So here, really what we're doing is The uncertainty of the forecast of the seasonal component, we're just ignoring those, right? So, and the reason for this is that you can see the uncertainty of the seasonal component is much smaller than the seasonally adjusted component. So it seems like a reasonable assumption just to ignore it in modeling here. And then just as an add-on, you can actually shortcut this with using the STLF function, and it works quite well. Anyway, you can play with both of them, and again, the data is included within the library. So hopefully this was useful, and I hope to see you in exponential smoothing starting next time.